Hi, sir.
Hello. 1 minute.
Yes, sir. Good afternoon.
Good afternoon.
Sir, everyone has joined and we can start now.
Okay. All right. You can record this conversation.
Yes, sir, I'm recording.
We'll just go over the questions. First, we will go over that.
So now I have sent a mail with both all the questions from Satish and Pooja.
Also, I had actually replied to some of that question. Do you have that answers as
No, sir, I haven't received anything.
well? Uh, so can Yajna and all in that Teams interactive group, right? That internal discussion, there should be that questions with some of my responses. Can you bring that up? Any of you, Sridhar? You have that?
Yes, sir. We have.
All right. First 2, 3, 4. I think these questions are clear, right? Any doubts you can ask in that. Number 5 also, I think I have answered. Just scroll down. Yeah. So 6, I have not typed it, but I had recorded. So we can one of you type while I explain to everyone? Until this point, up to number 7, are the answers clear? We can revisit question number 5 if required. So just question number 5, I am reiterating. How to resolve congestion? The answer should be first, improve on the floor plan. Okay, avoid module splitting, right? Look at, crisscross on the, you know, pin or feed throughs, and so improve memory placement, and check for any utilization growth, etc. Right. So that is one thing that we can do on the floor plan front. And second thing is, if you are seeing at the input netlist itself high number of complex cells, then you can give feedback to the synthesis. You can hide those cells and resynthesize, or look at DCT or DCG synthesis. That is another improvement that you can actually try. Sometimes congestion is because of aggressive IO timing. If you're seeing near IOs, the cells are all clustering too much, then you can actually relax the constraint or even actually look at, um, adding layered blockages. Okay, screens. So you can add that. Um, the next input is on the congestion. Can you go to that? You can also look at, in case your transition time is very tight. Okay, you have set something like 200 picosecond or something. If you are seeing your utilization jump is happening because during buffer insertion, a lot of buffers are getting added or areas cells are getting upsized. You should also look at, reducing your transition time. So that's also another aspect to look at, uh, your congestion or utilization growth. Uh, from the DFT perspective, I told two things. One is you have to enable scan chain reordering. If it's not enabled, it could actually impact. Second, you can look at macro grouping for MBIST insertion. So these are two things that you can try to improve on the DFT side for reduction of congestion. And if you have over constrained, your DFT constraints, from a realistic timing point of view, you can look at that aspect also. So add more realistic constraints. Power grid issue, the point is basically if you have added too many power steps than required, right? Which is actually impacting your congestion, then you can relax them to an extent. You have to do an IR drop, just do a dirty route and check if there is your power grid is actually too robust or too intense than what actually is required. So then you can actually relax your power grid, to do the right kind of stuff. So floor planning also, if your memory orientations are not right, which is causing congestion, that can also cause you issues. So those things you look at it. Library choices I have already told, right? You can hide high density cells in case they are causing issues, etc. And flow issue, from flow point of view, if your low power construction is not proper, or you are saying that uh, uh, the flow is set for very basic level, then you can improve on the flow by adding hyphen congestion options. You can look at if too much of buffering is happened, because internally there are some issues. You can review them, and also sometimes the tool versions also can be problematic. So look at that from a flow point perspective. And cell density and pin density, you already know how to resolve them. If you have high cell density, then you can add density screens. If you have pin density, you can look at adding you know uh, like module or cell padding, and resolve them. Any question on the congestion resolution? You edit these answers properly and then you can put that. Okay. So inputs to CTS. Okay. Before you do clock tree construction, you have to review your database and make sure your CTS mux placement, all the pre-placed cells, in terms of the clock tree are proper. You should ensure that before you do CTS, all your clock cells, all your CTS cells are of type clock cells, because you have actually bad cells. You have a data type cell in your clock tree, then all the constraints you would give in terms of adding CTS cells would not be properly honored sometimes. Okay, so ensure that is actually taken care. And ensure that if there is MPCTS, the multi-point pins are placed properly. If you have actually TMAC, make sure they are all properly under the uh, you know power mesh, etc. So all this should be taken care in terms of pre-placement. Next is, in terms of clock exception file, you are providing your float pin wherein you want actually clock balance point, then you can actually define them and put a float there and put whatever is the clock balance requirement. If you want to stop clock construction beyond that point, add a stop pin and exclude if that clock tree balance is not required and it's actually overbalancing them, because they're not really important from skew point, then you can use an exclude pin. So use the exceptions properly and add proper DRVs, clock DRV and which clock constructions need to happen. Um, the other thing is, you have to give the proper metal layers to route for the clock tree. Try to use higher metal layers for the clock, major clock instruction, and provide, uh, uh, double width single spacing as a start, but sorry, double spacing single width. But if there is enough route available, and because double width also would mean that a lot of latency and buffer levels are getting added, so you have to provide proper, don't over constrain in terms of by adding 5 picoseconds skew, etc. Be realistic so that you have to do some trials. If adding insertion delay and transition time, your transition time should be like between 8 to 12.5% around that. um, if you see too many buffers getting added also, you can relax it slightly, but don't relax the transition requirement below 20% of your clock period, um, or like 100 picosecond around that, so that if your clocks are sharp, then you will have a good data database. Mm, add aspects like fan out. Um, so no issue with that. Mm, so post initial clock construction, you have to look at how many clock cells were added. So roughly you have like 100K clock flops. Then you should expect anywhere between 3K to 5K clock buffers being added into your design. If you are seeing more number of clock buffers getting added, like 20K, 30K, like 20%, 30% of your cells, then there's a problem. Okay. You have to look at, which corner you are constructing the CTS. So as I told, you can start with mostly in the setup corner, but also analyze your clock insertion delays and skews in your fast corners also. So at least these two corners you have to analyze so that your clock tree is estimated. Because if the skews are really bad in the fast corner, then again your number of hold buffers getting added will be very bad. Your CTS balancing may not happen properly because the scaling should happen. If the scaling is proper, then it's good. You should check the level, number of levels of logic in the clock tree. If the clock level buffers are balanced, then your nets will be balanced. Otherwise you will see in the worst case, the clock skew is good, but some of the cells have been, some of the clock skew has been managed by detouring the clock routes. Okay, it could happen like that. Then you would see that in the fast corner, your balance would have gone off track. So ensure that the net delays and the cell delays are also balanced across the slow corner and fast corner. So these three aspects, um, the buffer levels, the net delay, cell delay should be relatively similar. Buffer levels would be the same whether it is slow corner or fast corner, but you should also look at the cell delays in the fast corner and slow corner and net delays and do a comparison, so that the net delay is not compensated with cell delay in one corner, which would actually make it bad balancing across corner, and that would impact your quality of timing. Okay. So analyze the congestion as well post CTS and make sure if there are a lot of short routes, CTS routes happening in the lower level layers, which is going to cause you both crosstalk and congestion, then you have a problem. So should have majority of the tree constructing in the middle layers. So that's another analysis that you have to do. So look at all these inputs, your CTS exception file, your clock spec file, what tree, which ones you need to construct, and also your you know uh, clock balance points. So all these you have to check properly, which metal layers, etc., etc., and ensure that they are all done properly. Okay, and construct the clock tree for the fastest frequency. First the function mode, then you can actually append it with the test test clocks by doing stub routing, automatically it will do. So first construct the main clock tree for the whichever has maximum number of flops, then you can start building the rest of it in sequence. So build a proper script for your CTS. Is that clear? Any questions? Okay, so that's about the answer to the question number 6. Now moving to the question number 7, if setup and hold is met and skew is present, then can we proceed for routing? Okay, if yes, why? If no, why? So there's no perfect answer to it, but I will answer both aspects. So if the setup and hold is met, okay, but you have actually good enough time, okay, then for your CTS quality, matching the skew across corners is a good criteria to have, because what happens is if there are variations happening, in future, that can actually have an impact in terms of yield. Okay, so even though setup and hold timing is met, it's a good practice to actually balance the clock skews, so that across corners, and in future wherever it would happen, that will actually help balance timing. Okay, and balance, minimize the variation. It will improve your yield quality. But if you are actually um, you know and sometimes you would have used useful skew to actually fix timing, whether it is setup or hold. Okay, so in which case, with minimal impact or minimal utilization, you could have still met that. So there you would really require, you would not bother about skew but still proceed to your closure. So that is also a valid approach. So depending on what is your quality of your design, you need to deliberately skew and still match timing. So your priority is your timing, but if that is met and you still have opportunity to improve your skew, you should do it, if the schedule and QR permits. Otherwise, you can proceed for routing. Is that clear? Is it clear? Any doubt?
Can you
Hello,
repeat once?
am I audible?
Yes, sir. Can you repeat once, sir? No, means if setup and hold is made, both are there, then we need to, if is there, time is there, we need to balance the skew, or else we
Yeah,
can
exactly.
proceed with the route.
Correct. If there is time and if your quality is going to improve, then you should try and balance the skew. Okay, because across the corner you will see your yield getting improved.
Okay, if we don't have time also, we can go with that.
But you would have sometimes used useful skew, right? You would have added deliberate skew to meet your timing, whether it is set up or hold, right? In which case it is required. Okay, and if you don't have time, and if your setup hold is good, you can proceed, no problem. Okay, because that's your first criteria. But skew balancing is more to do with improving the yield, etc. Okay, so you both.
And one more,
Yes.
sir, if we have utilization is good, then we can go with that, right? If we have time also.
Yes. If your time, if your utilization is not getting impacted, if your setup hold is met, you should try and actually try to improve the skew. If that approach, if that actually, if that possibility exists for you. Okay. Because
Okay.
that will improve your yield. Okay.
Mm.
And there's also one more aspect, right? If the sometimes what happens is if the skews are tight, everything is there, then again all the clocks would switch at the same time. Okay. Sometimes what would happen is there's also an approach, low power approach, that you can actually you don't have to switch, if your time permits, then even to improve your power, you can add deliberate skew. So there are actually aspects like that. The door locked, la? The door. எந்த door காட்டுறியா? எந்த door? Hello, am I audible to you guys?
Yes, sir.
Okay. So any more questions?
No, sir. Related to that question, we don't have it. You have it now?
Okay. Next is clock exceptions and its uses. I told you, right?
Yes,
Float.
pin and stop pin.
Yeah, float pin when you have actually built already small clock trees. Okay. And you want to balance that with reference to some skew. Then you can define float as that pin and say what is that early clock that you would need at that point, and then float pin. Stop pin is you have already constructed same thing. You have constructed a clock tree, but you don't want actually that clock tree to be constructed. See, then you would actually define a clock not to proceed beyond that point. You would put a stop pin there. Okay. The difference is, you know, in the float, you will give the clock balance that is required at that point, and it will do. It will try to, for example, you have a 2 nanosecond of insertion delay target, and there's an internal construction. You are expecting 200 picoseconds something to happen while you are doing top level construction. You'll say float, and then you would define, but still the internal clock may get constructed. Some things may get touched, but in a stop pin, the clock will not proceed beyond that pin. It will not actually construct anything beyond that pin. It will just stop the clock tree construction only till that point. Do an internal clock balance where you have actually given some early skew or something. That cannot happen in a stop pin case. You understand? And for a exclude, okay, you want that clock tree not to construct that particular branch not to be balanced, or you don't really care about balancing that. Then you will say you exclude the branch from, or you exclude this clock from any clock balance requirement, because
ఏమవుతుందంటే ఇంకా రిక్వైర్మెంట్ ఉందండి కన్స్ట్రక్షన్ వెళ్తుందంట అది స్టాప్ మంచి స్టాప్ అని పెడితే
The float pin means whenever branches will come, sorry, blocks will come at that moment, we can use the float pin to avoid that.
Sir left, I think.
I think so. Internal delay.
Suppose you into main part, into each part. Maybe half and into the new. I am real to it's imbalance level, things. We call the simple list. And macro inner macro internal leader and improve this imbalance.
Hello. Am I audible?
Yes, sir.
Yes, sir.
Yes, sir.
Okay, okay. All right. Um, let's look at the next question. Shall we move to the question number 9?
Hello, sir. Can you please
Sir,
explain me
last three exceptions,
float
you are
pin
told only 3 only.
again?
Yeah, there are only 3 exceptions. Clock 3 exceptions.
The stop pin, float pin, and exclude pin.
Exclude pin.
Yes.
Then what about
Any
this?
doubt?
Don't touch tree, non-stop pin.
Huh?
Don't touch tree.
Thanks.
So don't touch net.
See, basically, I will take, I'll give you, don't touch net and all, is like for what you have already built. Okay. And clock stop pin, you have to give the pin from which that branch, right? So which will, beyond which it will not actually build any clock tree. Don't touch net is, like for you have built some custom clock tree, right? And you don't want that to be touched. Then you will say, don't touch. Okay. You understand? Do you understand?
Okay. Yeah, yes, sir.
Okay.
Yes, sir.
Okay. So you want some special requirements, like you have added, some branch where you have actually added shielding, etc. So this clock tree is custom built. Then you say don't touch. Then it will not touch that clock tree. Okay, that's the point. Okay. There are other things which we can actually I can explain. Like clock stops and we can talk about that, some other stuff, because that will need some explanation. But majorly, from an interview point of view, I think these are good enough. Okay.
Recording out in the
Hello, Pooja, you are trying to ask something?
No, sir.
No, sir.
Okay. Nupur, are you clear?
Sir, actually floating point, I didn't get properly. I didn't
Okay.
understand. Mm.
All right. Can somebody explain to her what is floating? I'll see if people have understood.
So floating pin means whenever macro will be there or IP will be there, before that sync pin will be there. We can make that one float pin to balance the skew. Is it correct, sir?
Yeah. So yeah, but why? So basically, you are right. It can be used for macro pin. But the point is, see, by definition, right? You want to actually add a clock balance point. Let's say you have built a small tree, right? Just like what is built inside macro, or you want to do an early clock for this point. Any point beyond which you don't want to actually where you want to actually balance. Like for example, a small tree is built, okay, but some macro or something internally, then you want to actually like you have defined a mux point. That mux you want to early clock by let's say you have a total insertion delay of 2 nanoseconds, and at this mux you want actually a balance point of 1 nanosecond, so that you are assuming that from that clock mux output onwards there would be 1 nanosecond clock construction already done, or something it is actually going to do. Then you can define that as a float float pin, and you can define the clock balance that you need actually 1 nanosecond. Okay. On the same point, if you have actually said that that you should not touch beyond that any clock construction, then you can say don't touch after that, and then you will define a float pin of 1 nanosecond. Then what will happen is the overall clock balance will happen at 2 nanosecond. Then for this it will do at 1 nanosecond, assuming that hey, this is a float constraint you have given. Have you
Okay.
understood?
Yeah, sir. Understood.
Yeah. Okay.
Okay, sir.
Okay. uh let's look at the next point. So the next question is clock spec file details. Clock spec file, as you will have actually NDR definition, right? What are the non-default rules? Then you will have actually any specific requirement like which metal layer to clock route, which clock cells to be used for your clock tree construction. So all this will be part of your clock spec file. Okay, what is your clock skew and what is your clock insertion delay requirement? You understand? So these are the ones that you have actually in the clock spec file. Is it clear?
Yes,
Yes,
sir.
sir.
Should I repeat?
No, sir, it's fine.
Okay. Yeah. So then I assume it's fine. Okay. So if crosstalk is there, can we tape out? If yes, how? If no, why? Okay. So your timing is met. Crosstalk is a phenomenon which will anyway exist, right? In any of your latest design, crosstalk is a given phenomenon. Already that is already accounted for, and your timing, whenever you have actually doing, it's basically including crosstalk. If you have met the timing, you don't have to bother about any fixing additional crosstalk in your design. Okay, you can move forward without worrying about it, as long as your timing, transition, etc. are closed, and then you don't have to really bother about your crosstalk because that is expected in your design. You understand? Okay, so you can move forward with that.
But sir, it impact on functionality also, no?
Anyway,
No,
crosstalk will
crosstalk
be there.
noise also you have fixed, right? So the expectation is your crosstalk noise is fixed. If you have time, to do some clock spreading, you can do. Okay, only if you have time, you will try to improve, but otherwise you don't really bother about it. You understand?
Yeah, okay, sir.
Crosstalk noise has to be fixed. Crosstalk timing, double switching. All these are effects of crosstalk which needs to be improved. In addition to that, there are actually aspects like overshoot and undershoot. Okay, those generally you don't really worry, but they have impact in terms of adding noises to your design. So, but yeah, only if you have time you will try to improve that, but otherwise you don't really bother about because your timing is all closed. Just because of crosstalk, if you're touching anything, again some other timing pop-up will happen. Okay, so that's the idea. What's the next question? What is transition violation and its fixes? Okay, this question I have answered it so many times.
Buffering and long net is there. We can break that net and we can insert one buffer to make the transition phases.
What is transition violation? Can someone explain?
Transition violations means cell to cell net delay is too long and it take more time to deliver the signal from one to one.
Um, okay, somebody add more clarity.
If net delay is more,
So
then we
let us
can
first talk about library transition violation. What is library transition violation?
library transition to shifting from one logic to another logic to take time.
So what is how is it violating? When do you call it a violation?
Means actual means it will transition time usual than more it will give, then we can tell as violation is means transition violation happened. For example, if cell delay
More
is
means
2
what?
ps,
Huh?
if cell delay
Delay
is
is
2,
2
if cell delay is 2 ps, more than 2 ps, it will give like 4 ps or 5 ps. We can tell us that cell delay is having more transition value.
No, nothing, not like that. That's not the issue.
Duty cycle.
What duty cycle?
If duty cycle is more, then in that case also the
Duty
transition
cycle
value
is more means what?
setting is what?
What is
Logic
duty cycle?
to
There is
another
a
logic.
there is an aspect of duty cycle, but it's not coming out clear what exactly. Okay. So let's take first the example of a library. Okay? You can open any of your .lib if you already have just opened a .lib. And let's say for the cell, the characterization right? It's in a matrix. The delay table is given in the form of a matrix. Okay. So on the top is the transition. Okay. Horizontal x-axis is transition. Y-axis it is cap. Okay. Let's say the farthest the transition value mentioned is like 0.6 nanosecond. Okay. If it's like 0.6, then okay. Anything if your transition of your cell is beyond 0.6, okay, then it will say it's violating transition limit for that cell, because after that 0.6, whatever, because in between it's doing interpolation. After that 0.6 value, if it's 0.7, then the characterization table is not available for you. Do you understand? The when the delay calculation happens, it does not know what is the transition for 0.7. There is no value for it to actually work. What would be the delay? So what it will do is it will do something called extrapolation. So you should already have studied mathematics, interpolation and extrapolation. Interpolation is good. Okay. So, but extrapolation, you know, is like adding more pessimism, and that's not a right approach. So, extrapolation means you would never be able to accurately predict what is the actual cell delay which would happen. So, so that is the first violation which we are talking about, the characterization table, and this will vary for cell to cell. Okay, sometimes one cell may have a characterization which may be characterized up to 1.2 nanosecond, but for some cell it would have been characterized up to 600 picoseconds. So you'll have to be, concerned about that. So that is about characterization issue with regard to transition violation. The second aspect of transition is, as I said, right, now with regard to the frequency. Okay, what is this with regard to the frequency is, let's say you're running a design at 1 gigahertz. Okay, the the transition table may have actually a transition value up to 3 nanosecond also. So library would say you are not violating the transition of that. But here is a point where you have a data transition which is given, like, let's say the characterization table is 10 to 90% of the library. Okay, when you say 10 to 90%, that means the transition which is measured in your, by prime time or your tool is between the 10% of your logic value to 90% of the logic value. What is the time that the transition is actually taking to move from 10% of your logic value to 90%? Okay, and if this time is actually beyond your control, right? And now trans is actually taking 9% is taking actually, let's say, 1.2 nanosecond. So then in reality, from 0 to 1, it is like divide by point 8.
Sir, your voice is breaking.
That is 90 minus. My voice is breaking.
Yes, sir.
Hello?
Ah, yes, sir.
Okay, I think travel. Then I will stop here. Once I reach a stable point, I will. We will have a call.
But now it's
Okay,
clear,
I'll
sir.
answer other questions. Is it clear?
Now it is clear. Now it is clear, sir.
Hello? Okay. So as I said, if your transition table, if your library table is 1090 or 8020 or 7030, okay, 1090 means it is 10% of the logic value to 90%. 2080 means it's 20% of the logic value to 80%. So what you have to do is you have to minus the, let's say 2080 means 0.8 minus 0.2, 0.6. So the actual transition, whatever it is saying, like it is taking 1.2 nanosecond. It's basically 1.2 nanosecond is the time taken from 0.2 to 0.8. So for the 60% of raise is where it is actually taking 1.2 nanosecond. That means if it is 0 to 1, that is the logic level actually you are supposed to measure. That's the actual transition. So you 0.6. Right? So because 0.8 minus 0.2 is 0.6. So if you say 1.2 divided by 0.6, now your transition is going to be 2 nanosecond. Okay. Your frequency is supposed to be 1 nanosecond, but your transition is taking 2 nanosecond. How will your time window pass that, your frequency window? So you cannot actually have even though the library is characterized for 3 nanosecond, your frequency would limit the transition to maximum of 1 cycle for your data and for half the cycle for your clock, because that's the duty cycle where you will actually try to track. So you should look at your data transition should not exceed that 1 nanosecond. So what you will do is you'll have to actually put a data transition max as your transition time. Okay. So you have to compute like that. I will explain. So don't have more than 50% of your clock frequency. If your transition is actually violating more than 50% of your clock frequency, then that's a real violation. You have to fix all those transitions which are actually exiting, which are actually more than 50% of the clock frequency. The clock frequency again depends on that net. So some nets may be slow nets. Okay, you should not go by fastest clock in your design. Whatever that data net is supposed to switch, that's the frequency you have to take and accordingly compute the transition for that from a frequency point of view. Is it clear? So there are two aspects. One is characterization of the library. Second one is your frequency uh, of your net. Whatever is the switching, so at least your transition should be less than 50% of that frequency of that net. Have I explained it? And your clock should be 25%. Okay, maximum. That's the that's how you need to actually understand. Hello?
Yes, sir.
Hello? Am I audible?
Yes, sir.
Yes, sir.
Okay. Is it clear? If you have doubt, I will draw and show you. So maybe next time you have doubt, you can ask me. Again, I'll explain. No problem. Okay. So the second part of the question is how do you fix it? So transition fixes, you already know, just like, any upsizing or if the net length is more than, um, 500, 600 micron, etc., you will just buffer them. Okay. So depending on, whatever is the best approach, you will go and fix that, transition. So upsizing or buffering, right? Or if the transition is because of your crosstalk, okay, bad transition is because of your crosstalk, then you will move the aggressor net away from that, victim, which is where you are actually seeing bad transition, or move the victim net itself away from that aggressor. Whatever works for you. Those are type of fixes. Number 12 is spare cells. Spare cell uses. Why do you use spare cells? Anybody?
If you want to make any changes in the design
Hello?
at the later stages.
Spare cells, at the end of stage, whatever we want to change anything, we can use spare cells, like to replace the cells what we want.
Functionality will
No,
remain the same.
ECO cells are different. Spare cells, basically, yeah. See, spare cells are for ECO. Okay, you should not try and use spare cell for your timing fixes. Okay, that's not the purpose. Then you are defeating the purpose. It should be the, in case something is not available, then as a desperate means you should touch the spare cell. Otherwise, spare cells are supposed to be reserved for the functional ECOs. You understand? So in case there are actually some functional failure, the front end team says, I have this, then they know where the spare cells would be located in that. First of all, spare cells, you will add them in the matrix fashion. I have already explained this, right? Either in different locations, or you will actually put a spare cell, use some tool options to spread it across the block. Then, so that the designer can use the closest one to do the ECO. Okay, it's supposed to be reserved for the functional ECOs only, mainly. In the worst case, you can take their permission and use them for your timing in case you don't have any other ECUable cells nearby. Okay, that's the purpose. Sorry?
Sir, one small doubt, like nowadays we can add cells in any part of the design. Means if you want to add any functional cell like AND gate or gate, we can do it directly, right?
See, that's what is ECUable filler cell. Okay. The problem is, spare cells is an addition to that. By design that I have actually some functional failures coming. See, ECUable cells are more, there are going to be functional failures in this part because it's not verified properly. Okay, so I have some issues in this. Then they would add some dummy cells. The point about ECO and spare cells are different. In the spare cells, you would not connect the input and output, you will just leave them hanging. ECOable cells will also add leakage. Okay, but in case there is ECOable cell only wherever the space is there, the tool will add the fillers. But spare cells is by construction, you would have inserted the cells in that region. Okay, you would not give the choice to the tool, right? You understand? So it's a pre-fill. Spare cells are by design, you would actually insert them because this particular logic will have actually as potential failure paths. Or for your first release, you have actually done some masking, software masking, so you don't really have triggered those functional paths, which you expect that to be done in the next version. Just because you have to do another version, you don't want to actually open up all the design, redo the entire chip. You can do just the BOL instead of doing the FEOL process as well, so that you would minimize the number of mask cost construction. So those are aspects one takes care in the architecture. So that's why spare cells are inserted.
And is there any like specific percentage that we insert 1%, 5% like this, or
You should not know. As a physical design, you should never allow the front end to add actually more than 0.1 to maximum of 1%, because adding more spare cells would actually limit, because they would all be given specific regions, or you would put them fixed, then it will impact your QR. Okay, so it's not expected those spare cells also. That means it's a low quality design. You would say, hey, if you are going to do so much of pessimism, then there's a problem. Okay, so it should be very clear about that. And what would constitute spare cells are, again, there should be at least one inverter in any spare group. In case flops are required, you would actually add maybe, but I want to add one NOR gate, one NAND gate, one inverter. These are all basic things so that you can construct any other cell required. Okay.
yes?
2x drive, 1x drive, low drives you can keep. Okay. So decent things will be there. Okay. That's about it. What's the next question? UPF, and what is there in UPF? UPF is a uniform power format, either it is UPF or CPF. So that is supposed, huh?
Unified power format.
Yeah. So basically it's to define what should be the low power implementation. What is that, the way the different power groups are supposed to be. So any implementation in terms of multi-power domain or any shut-off domain, all those will be actually be specified in terms of the UPF. And this is a key file which will actually define your methodology and your power checks, specific to that. So what will be present in UPF is which power domain connects to what, okay, and what are the specific kind of if you want some specific level shifters, you can define them. you can define basically all the power connectivities and isolation, type of isolation required, whether it is AND isolation, OR isolation, etc. All those things has to be defined in the UPF. Okay. Synthesis basics and tools. So synthesis basics, I have already told you, it will convert your raw TL specific to the technology. Okay. By while meeting your timing and utilization constraints. Okay. So it has to meet your all your physical and timing requirements while porting to the technology. So that's the idea of synthesis. And again, there are three basic steps: analyze, elaborate, optimize. Okay. So that is also there. And then, there are actually types of synthesis that you can do: logical synthesis and physical aware synthesis. And also third one is congestion aware synthesis. So logic synthesis is basically where it wouldn't do any placement. It wouldn't actually, it will just look at what is the fan out and what is the wire load model, and based on which it will just go and do a logic synthesis. It's not aware where it is connected, how far it is from the next cell, next flop, etc. It won't have any of that. But physical aware synthesis is going to be aware of your flow plans. Again, you can run physical aware synthesis in two different ways: using the def file and without the def file. Without the def file, the tool will automatically do some placement of your macro, whatever it is, but it will do the placement, and accordingly it will do the synthesis. It will estimate what is the net capacitance, and accordingly buffer them, do high fan out net synthesis. All this is possible in physical aware. And so and in floor plan def, it will also consume whatever floor plan, like your macro placement and your blockages and your power routing. If you have fed all that, it will read that, and accordingly it will do that physical aware place and then do the synthesis. Okay. So those are aspects about synthesis. I think at a high level you can answer this much, so that should be good enough. Tools, as I said, synthesis tools. If it's synopsis, there is DC, for logic, DCT for for physical aware, DCT SPG for physical aware with floor plan information. You want IBM tools, you can talk about Bulldozer. You want actually Cadence tool, you can talk about Genesis, okay, Genus, and RTL compiler, right? So things like that. So there are those are the tools. TCG is again, congestion aware synthesis. What is electron migration and its fixes? What is electron migration?
Due to high
High
current
current
density,
density, some electrons will move, replace displacement and have making shorts or opens.
he loves and avoids megaphone.
Sorry.
Due to high current density, some atoms or electrons might replace and it make opens or shorts.
No, wide and locks.
Wide and locks.
Wide and lock.
Inside.
What is that? Widen. What was that?
I don't know, sir. These people are telling that wide and something.
Wide and lock.
Create a void and other place a lock structure.
Opens and shorts.
But they expect wide and lock.
Terms will be-
See, you should use the word hot electron effect. Okay, what happens is electron migration is not a immediate phenomenon. Okay, it's a constant bombarding of your, because of valence electrons and cells actually moving, right, due to frequency of operation. So there is frequency of operation and constant bombarding of the cell. There is a hot electron effect. And what happens is in the surface, okay, when there is constant bombarding, the wire can actually rip off. Okay, so that particular net, when it gets ripped off, maybe a part of the net gets ripped, but it can touch to the next metal layer, causing short, or it can completely rupture. Then it can actually cause a open. So this electron migration is a aging factor due to hot electron constant bombarding of the cell and the speed which it operates, and so because current of high current, aging. So all these are factors. So principally, there are all factors contributing to the hot electron effect. This rupture, okay, and that rupture can cause shorts or opens. Okay. Now the solution. What are the solutions? What are the fixes for the electron migration? Yeah.
Increase the wire means double width. Width of the net.
Net. Metal.
Okay, that is one solution. What else can you do? Let's say in that path you don't have, you cannot double width. What else can be?
Higher metal layer. Raise the wire width.
Okay, higher metal layer. Okay, what else? Hello?
Yes, sir.
Any other solution? Huh?
Increasing the number of straps.
Increasing the number of straps. How is increasing the straps going to help you reduce the electron migration?
Like instead of one net, we can use two nets to supply the voltage like that.
Power EM. You're talking about power EM, or you are actually talking about slotting. The net can be split, make it multi-drive, two routes. Is that what you're saying?
Power only.
First, talk about signal EM. How are you fixing? We talk EM in different aspects. Signal EM, you said increase the width or move to the higher metal layer, basically where you can actually pump in more capacitance. Other than that, what you can do is you can downsize the driver so that the current supply from the driver reduces. That's the reason why you are actually not using big buffers, right? You are not supposed to use 24x or 36x clock buffer, because that will drive high current and it's going to cause you EM violation. Hello?
Yes, sir.
You get the point?
Yes, sir.
Okay. The next fix is basically EM can also happen because of high fan out. Okay. You're driving 40, 50, and then you see that the driver is adding, because of which you have to add a big driver. Then you can do split fan out. Okay. By splitting, again the current requirement for that is going to reduce. So these are, other than the net, downsize the driver, and actually fan out splitting is all the other techniques to fix the EM violation for the signal EM. Okay. For the power EM, you can actually add more straps. Okay. You should think in multiple directions. Just more like reading like history books. Okay. So that's about EM fix. shorts DRC, I think you can answer that, we can use aggressive fixed DRC. We can look at, wherever cell density is high, we can, reduce the density by adding density screens, etc. So all that fixes basically whatever congestion alleviation. Or if you are seeing more shots in particular metal, you can give route guides. You can look at all that. And tool specific also, you can do aggressive fixed DRC. There are so many tool options. We can talk about that. But anything specific to technology, if they ask, then you explain it. Setup and hold is there in same path. How can we fix? I've answered this question again. How will you fix if setup and hold are there present in the same path?
We can adjust the clock path.
If the clock paths are different for the setup and hold, then you will adjust the clock path accordingly. Yes, that is one option. What else? What are the other reasons?
Sir, is there possibility for setup and hold both the same clock path and data path?
Oh yes, it is a true possibility. Same data path can have setup hold violation. Okay.
Data path same, but clock path also same will be there.
See, if both the exact clock path is same for the setup and hold, okay, this also can happen because if your cell delays are varying across the clock, across the corners, okay, like 7x, 8x, cell delay in setup corner is 100 picosecond, but in the fast corner it's only 10 picosecond. Okay, that's one reason, and that can cause actually very fast crosstalk. Okay, so I've already told you crosstalk, clock skew, right? You have actually cell delay varying, too much between the corners. Okay, and clock reconvergence paths are different. All these are causes. Okay, and depending on whatever is the cause, you'll have to fix it accordingly. Is it clear?
Yes, sir.
Can hold occur at placement stage?
Due to bad constraints, we will get the hold violations in placement stage.
Yeah, at floor plan level, yes. But let's say floor plan it's clean. If the answer is floor plan it is clean, can it come at placement stage? Okay. The answer is still possible. Reason being that, I'll tell you the clock transition value should be set. Okay. If the transition at the data pin is actually really bad, okay, very, very bad, and then, then you will see that, that particular D pin, because of bad transition can show like, at the clock pin bad transition. If not set, then it can say hold requirement can become like 2 nanosecond, 3 nanosecond, and it can show violation. Okay. So that's another perspective. Okay. So it can come, and that is basically because bad constraints or sometimes bad transition on the clock pin. Okay. So this can happen at placement. Yes. Okay. If yes, we move to next stage. If not, why? Okay. So basically, it's a feedback for the constraint that you should actually try to clean up. Okay. You should clean up, because it's going to have a next stage impact. CTS anyway, that will be seen. But even if there are violations which are genuine, which is a genuine violation for which old fix have to happen, you can proceed for that. Okay, you know it's a genuine violation. If there are no genuine violation, you should try and clean that up either in constraint or in the transition stuff. Only genuine violation, you should progress to the next stage. Non-genuine, you should clean up the constraint and move forward. Oh, sorry, 18 and 19, I think I missed. What is dynamic IR and its fixes? You know, right? What is dynamic IR?
When the cells are switching, voltage drop means
Yeah.
power loss will come. That
So when the design is in function, so they are switching, then whatever IR drop is accounted, they are actually dynamic IR. Okay. So when the design is in ideal mode, then there that is called static IR. Okay. So constant. So what are the fixes for dynamic IR?
We can use clock adjustment or decap cells. We can use for that.
No, decap cells, and what is the other fix you said?
Clock gating.
Clock gating.
Clock gating.
Yes, sir.
Clock gating for dynamic IR. Okay, that fix you cannot do. You cannot deliberately add a clock gate, right? How will you do that? Dynamic IR issue, if you have at the particular region, you can try to add a decap, or you have to move the high frequency switching. Okay. Cells from that domain. You will have to take that off. Whichever has got that IR drop, move the cell, spread the cell in that region. Okay. And if there are clock cells in that region, then try to see if there is a possibility of moving that cell away, so that switching would reduce. Okay. And the other option is you can actually see downsize some of the cell if your timing permits. If there is enough timing margin, you can downsize so that the switching is not as sharp. Okay. So these are the ways to improve your dynamic IR drop. Okay. Timing fixes order. What are the timing fixes order?
First VT swap. After that, the sizing
of the cell.
Any other answers? No, timing order should be, please write down again and again. I have stated it many, many times. So first thing you have to actually fix is clock tran. Okay. Clock cap, clock tran. Okay. Then fix data DRVs, data tran, data cap, etc. before you, right? So this should be your order, long length nets, etc. Then you go ahead and fix the setup. Okay, so and how you do the fixes, we'll talk. Then you will go and actually do the whole fixes. Okay, so after you fix the setup, you will go and do whole fix. Then you will actually cover whatever whole fix. If there are actually setup violations, you will cover that, differently. Now, what kind of setup fixes after you have fixed plan, etc.? Okay, so first thing should not be, if you are worried about DRCs, yes, you can do BT swapping if that option is available, but you cannot actually switch more than 1% of ULVT, etc. if they are actually constrained. Okay, you will try and so BT swap to have minimum routing challenges, but you will look at sizing then actually do the buffering, right? If the nets are far off, then first thing you would do, all the net lengths you will fix them first, long nets. Then you will actually look at I fan out. Then you will do those splits, and then you will take the sizing and buffering options. Okay, so this is your order. Even your whole fix order also you have to mention. Whole fix, first thing I will do is clock skew, right? Even your setup, you should try and actually play with the clock. So if those whether setup or hold, you'll first play with the clock to try and actually use skew to cover for maximum number of violations before you touch the data. And then in the case of hold, after you have actually played with the skew, the next approach would be start point fix. And once you have addressed them, the next point would be bottleneck fixes. Then you will move to the endpoint fixes. This would be your order of fixes. Okay. Is it clear? All right. I'll take a break now. We'll cover remaining of questions and move to the other part also.
Okay, sir.
Okay, sir.
No